So, last time we introduced the Jahn-Teller effect. And really we started talking about how delta O and really the bonding in the molecule, it kind of influences the reactivity of the compound and ligand substitution. We talked about metal to ligand and ligand to metal charge transfer and how that electronic transition kind of reflects the bonding of the transition metal with the ligands. The metal that's really strongly oxidizing is easily reduced, and it doesn't take very much photon energy to pump an electron from a ligand to that metal, and vice versa. And so we looked at the ligand substitution rate for aqueous transition metal ions, and the mechanism for substitution is dissociation of a water molecule first. Dissociation is the first step in the swapping of waters bound to the metal with those in the solution. And so the speed at which the dissociation happens is dictated by the strength of the metal ligand bond. Stronger bond, slower to dissociate. So you can look at the delta O you can look at the delta O and also whether or not the sigma star orbitals are occupied to measure to estimate the rate of exchange. So remember, if there is an electron in the sigma star level, then the waters are more likely to come off. Because when you pull the water off, the electron from the sigma star drops. So things like cobalt-2 hexaquo are high spin. They have electrons in the sigma star orbitals. The water substitute really fast. Cobalt-3, much slower. The classic conundrum in the study of aqueous ligand substitution kinetics is that cobalt-3 is too fast. I don't know, I think we mentioned that. Cobalt-3 is too fast. And it should be even slower. And the reasoning behind that is that actually there's a small amount of cobalt-2 ion in a solution of cobalt-3. And the extra electron actually hops from cobalt center to cobalt center in that solution. And so when the cobalt has the extra electron and is the small amount of cobalt-2, it does ligand substitution quickly, swaps all of the waters off, and then the electron hops to a neighboring cobalt and all of its ligands swap off. And so normally when you have cobalt-3 complexes, it's possible to do ligand substitution kinetics and ligand swapping reactions with them faster than they should because of that electronic swapping, that electron exchange thing. All right, and then we talked about the Jahn-Teller distortion. And I'm just going to remind you, because we sort of jumped from that relatively quickly last time. So we said in the case of chromium, we have a long bond and then some short bonds. And it has that structure because in an octahedral splitting, you will have one electron in this pair of levels that are degenerate. And the molecule can actually strengthen the bonding with the equatorial waters and weaken the bonding with the axial waters in order to lower its energy. So you lower the energy of the bonding electrons on the waters, right? We're not showing here, this is the sigma star level. There's also the sigma bonding level, which are really the electron pairs on the waters. Those drop because the waters get closer. And then this electron here, which is the sigma star electron, it drops when you lengthen these bonds. Okay, so the molecule distorts to achieve a lower energy structure when you have this electronic degeneracy, and that distortion is called the Jahn-Teller effect. Okay, so in order to understand that splitting, maybe I jumped too fast here. You know, in order to understand why these two move in the way that they do when you push and pull the waters onto the chromium and off the chromium, you need to know where those orbitals point, right? So you gotta, this is the latest challenge in all of this stuff for you guys. Where is the dz squared? Well, the dz squared is aligned along the z-axis, and I picked the z-axis along the long chromium water vector. Where is the x squared minus y squared? The x squared minus y squared is in the plane, the equatorial plane of these four waters, and it points at the ligands, right? X squared minus y squared points at the ligands. You got to remember that. dz squared points at the ligands. It's xy, xz, and yz that do not point at the ligands. Those are in between the ligands. So x squared minus y squared and z squared point at the ligands. And this lengthening along z will drop the z squared. The bonding gets weaker when you stretch the bonds. All right, so we're going to do that again here in another example. Before we do that, you know, when you do these kinds of distortions, this distortion strength depends upon the electronic configuration. So there's the following situations. High spin D4 T2G 3 EG once. So in that electronic configuration, you have 4 unpaired spins. That's a quintet, and a single degeneracy in the EG set. So it's an E. That's basically the case that we just did. Low spin D7. That's another one. T2G6 EG1. So this is a doublet E. There's only one unpaired spin. There's low spin D9. So here we have one unpaired spin and a single hole that we can move around in EG. So what do these all have in common?
Like a degenerate upper levels. Oh.
They have degeneracies, that's true, but the degeneracy is, or I should say, all of these systems have an electron in an antibonding level. Okay, the degeneracy is in an antibonding orbital. Okay, so if you have a degeneracy that's not in an antibonding orbital, you can't really fix the situation. Okay, so Okay, so let's do D1, T2G, 1, EG, 0. So we've got a doublet, and this is a T because you have one electron in a T2G level. T2G is triply degenerate, so that's a doublet T state. Now, why does that not, how do you fix that problem? Well, you could push and pull the ligands all you want, but that level is non-bonding when you only have sigma donating ligands. So the pushing and the pulling in the ligands does not change the energy of that orbital because they don't overlap. Same thing, T2G twice, EG 0, 2 unpaired spins, 1 way, 3 ways to arrange them. And then similarly, you can have low spin D4, T2G4, EG 0. So here, how many unpaired spins do we have now? Anybody?
1.
We have 2 unpaired spins, which is a triplet T. 1, 2, 3, and 1 more in one of those levels. So 2 levels have single electrons in them. So this guy again, degeneracy is in this non-bonding T2G set. Low spin D5, same situation. T2G5, EG0. How many unpaired spins?
1.
So that's a doublet. T. We have high spin D6. T2G4, EG twice. How many unpaired spins?
4.
4 unpaired electrons here. High spin D7, T2G5, EG twice. 3 unpaired spins, quartet T. Okay. In these cases, distortion can be driven by pi bonding. Because T2G has pi symmetry. Right? T2G is the XZ, YZ, and XY orbital, or orbitals. Those orbitals point between the ligands, and they can make pi bonds. They point like this. You have a p orbital on some ligand out here, they make pi bonds. So pushing and pulling on the ligands will strengthen or weaken the pi bonds, and that'll push the energy of that T2G level around. But if your ligands are only sigma donor ligands, then it doesn't matter. Pushing and pulling them, there's no interaction with T2G. You can't fix this degeneracy problem by distortion. Yeah? Okay. Anybody confused?
I am. Can I ask a question?
Yeah.
I know you told us how to decide like the levels of degeneracy, like we went over that last class, but I'm not understanding how you're getting that from just looking at what you're writing here, low spin D4, T2G4. It has 3T. How are you finding 3T just by looking at that?
Well, I know that this particular electronic state here looks like this.
So there's three different places that that electron can move right there in the lower orbitals.
This one right here.
Yeah, so there's three different places I can move that electron or that into those two other unpaired spots.
Yep.
And so that's where you're getting the three from. And so basically,
No,
you just know it.
right. That's where I'm getting the T from. This number here refers to the spin multiplicity. It's the number of electrons that are unpaired.
Oh, okay.
So there's
Okay.
two paired electrons, and therefore it's a triplet state. If
Okay.
there were
Yeah.
four unpaired electrons, it would be a quintet state. If there are no unpaired electrons, it would be a singlet state. So this guy has two unpaired electrons. That means it's a triplet state, and the degeneracy is threefold because this guy could be here or here. Three ways to write that down pointing an electron. That makes it triplet.
Okay. And you just basically, you know, D4 looks like that. That's the electron configuration. So,
Well, yeah, because I know T2G is triply degenerate and EG is doubly degenerate. Octahedral is 2 on top, 3 on bottom. So when I say electrons in T2G, then that's the only way to put them in.
thank you very much. Thanks.
Yeah. All right. Now let's take a look at some frontier orbitals and the transition metal geometry. Okay. So we're going to do an example today. Manganese hexacarbonyl cation. This guy is T2G6 EG0. Why is it low spin instead of high spin?
CO is a very strong field ligand.
Yep, it's a good donor and a great acceptor, and that makes that delta O really wide. So this level, the T2G level, this is D pi, and it's full. This guy is D sigma star, and it's empty. The D pi character drops it in energy. So we're going to add an electron to this thing. So now we go to manganese 0 hexacarbonyl. And this guy, T2G6 EG once, also low spin. This thing loses a carbon monoxide. And this product has C4V symmetry. This is spontaneous. CO pops right off when you put that electron in there. The question is, what does the MO diagram for that thing look like? So we have a manganese, a CO, we have our 1 electron reduction and loss of CO. And we're going to orient the z-axis along this way. We'll stick the x-axis over here. We'll put the y-axis over there. We're going to keep the same situation over here. So we can do a diagram like this. Where this is d sigma star x squared minus y squared and dz squared. And this is d pi xy, xz, and yz. Now, instead of just writing those things down blindly, if you're doing that, think for a moment about where the x squared minus y squared and the dz squared orbitals are. Where are they? Somebody tell me, please. Just blurt it out.
On the z axis.
Which one?
The dz squared is on the z axis, and then the d pi is like you just told us. So xy or xz and yz are pointing, like they're in the field of the page, right? So they're going to be pointing towards the ligands, whereas the xy is going to be pointing in between, right? In between the ligands.
So this level right here is x squared minus y squared and dz squared. And I've told you that it is d sigma star. That means that those orbitals point at the ligands and are making a sigma bonding interaction. So they're pointing directly toward the carbons, head to head. Okay? X squared minus y squared and dz squared point at the ligands. Now, x, y, x, z, and yz do not point at the ligands. They point in between the ligands. Their nodes fall on the ligands. And that's why they're pi symmetry, because then there's an internuclear node, nodal plane, right? So the xz, yz, and xy's fill up the spaces between the carbonyls, whereas the x squared minus y squared and the dz squared point at the carbonyls. So now, this structure on the right, what happens to its diagram? You popped off a CO along the z-axis. So let's do the sigma part first. Are these affected by that change? Yes, they are. Z squared is going to drop in energy. X squared minus y squared is not. Right? Because the x squared minus y squared points at these COs, and it still has 4 of them. DZ squared is here. It's missing a ligand now, so now it's not as antibonding anymore. Now, how about these ones in the bottom? What happens to them? Are they affected? Please use your voting. Raise your hand if they are not affected. Would somebody who did not raise their hand, please tell me why they are affected?
I think it's affected because XZ and YZ is required for the binding to the pi orbitals. So since we lose a ligand, so Xc and Yz will be affected.
That's right. So Xc and Yz are making pi bonds. This guy is d pi. That's a bonding orbital. You just lost a bond. So the product is going to have slightly less stabilized dxz and dyz. These guys are still pi bonding. And down here, dxy, it stays roughly the same. It's the one that's pointing between the COs here. Still has 4. But this guy, he lost one. There used to be a CO down here. It's gone now. So the Xc and Yz yeah, the Xc and the Yz orbitals are no longer as strongly pi bonding. So these sigma stars change and these pi bonding orbitals change. So let's put in some electrons here. Low spin D7. Low spin D7. This guy is a doublet E state. This guy is a doublet A. So you lose the CO, it lifts the degeneracy, you weaken the bonding with Z squared, and therefore the sigma star level goes down. You weaken the pi bonds, and therefore the d pi levels go up. So let's draw this thing out again. There's your dz squared orbital. That's the HOMO. And it has this single electron in it. That's a radical. It's not stable. This thing dimerizes. And the product is D4H. So you take these two unpaired spins on two different manganese centers and you make a sigma bond. Let's see what that looks like. So dz squared. This guy is A1 symmetry. And you make a metal-metal sigma bond and a metal-metal sigma star. 2 electrons down here. Oh, sorry. Now, it's not the only bond you make, actually, because you also have an x squared minus y squared up here. And these happen to be B1 symmetry. Where are the x squared minus y squareds? It points down here at these COs, right? The x squared minus y squared y squared points at the ligands. So when you put them together, they cozy up to each other, side by side, face to face. So what kind of a bond is that?
Delta.
That's delta. Who said that?
Me, Rachel.
Thank you. There's a delta and a delta star. Notice how much smaller I've drawn that splitting, right? That overlap is not nearly as good. Delta is not nearly as good as sigma.
I have a question here. So why is it not D for D? So in the other way, x squared minus y squared can make a bond with xy, and that is also a delta bond. So I guess is that like energetically less favorable? But on the other hand, CO and CO on the eclipse conformation is like more steric hinder. So I'm wondering if we have a larger ligand, is that going to change into like a D4D?
There's been a lot of work on this kind of thing, Brian, and what you're saying is exactly right. There's two different forms, so we're going to make a Newman projection here. This one is D4H. This one is D4D. And both of them can make delta bonds, actually, because there's also the XY orbital, which is in the same plane as the x squared minus y squared. And you can have a donor-acceptor kind of an interaction in this geometry along that when you orient it in that way. And so I think that this is the ground state structure. Okay. Let's do another example. Oops. Nickel 2 hexacyanide. What's the charge on this compound?
4 minus.
4 minus, because each cyanide is a -1 and the nickel 2 is a +2. So that's 4 minus. This is hypothetical. Okay. What's its splitting diagram look like? How many electrons does nickel 2 have? Got to know your periodic table.
8.
8.
There we go. 8. Nickel, palladium, platinum are D10. So the nickel 2 ion has 8 electrons. Or a sigma star and pi. So what does it do? It loses a cyanide because it doesn't like that much charge. When a cyanide pops off, there's no change in the oxidation state. We're just losing this anion. You can't go backward. And that puts us in the situation we were just looking at. We lose a ligand along Z. Z squared drops. XZ and YZ go up. And it happens again. You can kind of go back, but that structure is higher in energy at most concentrations. So this guy is C4V. What's the product of this thing? Well, it's square planar. That's D4H. So square planar D4H. So we lost another cyanide, and where did it come from? It came off of the Z-axis again. So what's going to happen? Well, the same thing is going to happen as it happened last time when we lost one along Z. X squared minus Y squared isn't going anywhere. Z squared drops even further, but it's still sigma star. Why is that? We just lost both ligands along the Z-axis. Why is it still sigma star?
Is it because the symmetry will stay the same, but like the energy might? I mean, it's just changing the energy when you drop it, right? But it's still going to have like the same type of symmetry that you would have for that particular orbital.
It has the same symmetry as the ligands, but it's funny that that's the case until you remember that there's this donut. The donut points at the ligands. The Z squared is not off the hook completely. Okay, it's still sigma bonding or sigma star because of the ligands. And the XZ and the YZ, sorry, there we are. Those guys are all still pi bonding. Now the XY is really pi bonding because it's got 4 cyanides with which to make pi bonds. The XZ and the YZ used to have 4, but now they only have 2. Okay. You could draw other geometries for these. Nickel pentacyanide doesn't have to be C4V. It could also be trigonal bipyramidal, which is D3H. Nickel tetracyanide doesn't have to be square planar. It could be tetrahedral. Then things really kind of change a lot. It turns out that things with really strong sigma bonders, they tend to like right angles because right angles are good for sigma bonding. When you're in tetrahedral land and trigonal bipyramids where you've got odd principal axes and stuff that's not at right angles, the sigma bonding doesn't work as well. The overlap isn't quite as nice. So strong sigma donor ligands like cyanides tend to prefer right angles. And that's why these compounds are C4V and D4H. Let's do an example. Go ahead, Rachel.
So across this the EG is the same energy as the x squared minus y squared, and the T2G is the same as the XY or the XZYZ? Or is that not analogous in general?
Let's redraw this just to make that clear. You're right. So the point is that, you know, if you don't lose an orbital or you don't lose a bonding or anti-bonding interaction, that the energies shouldn't really change. Or that's the point of the example, is to teach that idea. You know, the energy, position in energy is a measure of how strong the bonding interactions or anti-bonding interactions are. When you lose a ligand along a direction, you lose a bonding interaction, and that weakens the strength of that. You know, so the energy of that level moves as a result. If you have two hydrogen 1s functions making a sigma bond, you get a splitting. As you pull them apart, the splitting goes away. Okay? All right. Now, we're going to do D3H iron pentacarbonyl. This compound is definitely in this structure. So this is E2C3, 3C2, sigma H, 2S3, and 3 sigma V. And 5 ligand sigma for this guy turns out to be 5, 2, 1, 3, 0, 3. And we're going to do this trick where we take the XYZ to generate the pi's. We're going to use the trick that we used before. We've got the gamma XYZ. We're going to multiply it by the 5 ligand sigma here to get to our gamma total, which is a sum of sigma plus pi. So the product of these is 0, -1, 3, 0, 3. And that means that the gamma 10 ligand pi is 10 -2, -2, 0, 0, 0. Okay, so we generated this 10 ligand pi piece here, knowing that the sum of sigma and pi is the product of these two, right? So all we're doing is we're saying, you know, multiply an XYZ coordinate system by a sigma orbital at each of the positions of the carbon monoxides. And what does that look like? Well, that looks like an XYZ coordinate system on each carbon monoxide center. And then there's one of those is going to be pointing at the iron, and the other two are going to be making the pi bonds. So you subtract the sigma part, and then you're just left with the two that are making the pi bonds. Go ahead, Rachel.
Is there a way to do this for delta bonds also, or are you just kind of screwed for that?
So this is going to generate the XYZ coordinate system on each center. And those are the same pi symmetry orbitals on the carbonyls that make, so sorry, when you say delta bonds, you're now referring to metal-metal bonding between two, say, metal manganese pentacarbonyl units. Yeah, you could do a reducible representation for a sigma orbital on both manganese centers and then multiply by gamma 5D to the reducible representation for all the d orbitals. And then that would give you the sum of those. Then you'd have to break that out into sigma, delta, and pi components, if that's clear. I think it's not so bad. Usually we're only dealing with one sigma bond between two metals. If you had a little metal cluster, you could try and take that approach, but you're getting pretty fancy now. Okay, so the, whoops, 5 ligand sigma turns out to be 2A1 prime plus E prime plus A2 double prime. And the 10 ligand pi turns out to be A2 prime plus A2 double prime plus 2E prime plus 2E double prime. Now, you can't really do this by inspection. You know, taking a C3 operation and, sorry, back up. You can do this by inspection. Yeah, so this is actually no problem at all. This you look up, getting ahead of myself. It's the iron d orbitals that are complicated, right? This you can do by inspection. And we just say, all right, how many move? None. How many move? Well, only 3 move because 2 are on the C3 axis. 1 carbon monoxide per perpendicular C2 axis. There's 3 carbon monoxides in the sigma H plane, et cetera, et cetera. So you can do this by inspection. You can look this XYZ up in the table. You do the product to get the sum of sigma and pi, and then you subtract the 5 ligand sigma, and it gives you the pi. Okay? So let's make a diagram. Just leave that up there. So we're going to do 5 ligand sigma first. One, 2, 3, 4, 5, and we have 2A1 prime, E prime, and A2 double prime. Those sigma orbitals are going to mix with the metal here, which is 1, 2, 3, 4, 5 d orbitals. They are A1, E prime, and E double prime. And we're going to get some bonding. And there's no E double prime, so there's 1 that's non-bonding. And which one is that? What is E double prime, do you think? In this structure back here, we're looking at the d orbitals on the metal that do not make sigma bonds. And which ones are those? Z-axis is here. These 3 carbonyls are in the XY plane. So which d orbitals do not make sigma bonds? I know some of you know the answer to this, or you think you know, but you're not sure.
S squared minus y squared.
X squared minus y squared are in the XY plane. And so they don't really perfectly line up, but there's bonding. There's sigma bonding.
dxz and dyz?
dxz and dyz point above and below the xy plane, and they have nodes along the z-axis. So xz and yz do not make a bond with the COs. Their nodes fall on the xy plane and along the z-axis. So there's no interaction, sigma bonding interaction with the COs for those two. So this is dxz and dyz. Now the other two, E prime, x squared minus y squared, and xy, they are sigma star. And then dz squared is A1, and it is sigma star. So let me tell you a little trick to remember. When you have an odd principal axis, like we do in iron pentacarbonyl and D3H, x and y go together. Px and py go together. X squared minus y squared and xy go together. And xz and yz go together. Okay. In this plane over here, where you've got the 3 carbonyls that don't really point right correctly at anything, it's an odd symmetry in that direction around that plane. X and y are indistinguishable from each other. So the x squared minus y squared and the xy, they're degenerate. And the xz and the yz, they're also degenerate. Okay, and there they are. We've got an E prime for x squared minus y squared and xy. We've got an E double prime for dxz and dyz. All right, let's add some pi interactions. We now have to add in 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 d pi's, and these are A2 prime, A2 double prime, 2E prime, and 2E double prime. So first of all, there is no A2 prime or A2 double prime among the d orbitals. There is an A2 double prime among the sigma orbitals, but we're not talking about the sigma orbitals on the carbon monoxide interacting with the pi orbitals on the carbon monoxide. Okay, so I'm not going to consider that. I'm just going to say you have an A2 prime and A2 double prime out here that are non-bonding. Sorry. Now, E prime and E double prime, there is an E prime and an E double prime over there. And so these guys are going to go up. And really I should split them, but I'm just gonna worry about the d orbitals here. And let's take a look at what we got on this side. Okay, so we've got E prime and E double prime that come from sigma bonding, the sigma only picture. One of them is associated with the xz, yz. The other is associated with the x squared minus y squared and xy. So what happens when we make a connection now? Well, this E double prime is going to drop. The E prime is going to drop. And sorry, I didn't really leave myself enough space. I gotta say, this part of the job is really convenient. And that dz squared is relatively unaffected. So now we've got d pi. This one is interesting. It's both sigma star and d pi. And this guy is just sigma star. Really, I'm getting a little sloppy. I should say d sigma star and d pi. So notice how the pi bonding helps to stabilize those guys relative to the sigma only picture. So it's kind of cool. The dx squared minus y squared and dxy here, they are both sigma anti-bonding and pi bonding. xz and yz, only pi. And then z squared is still doing its anti-bonding, sigma only anti-bonding type of thing. So remember what I was saying about right angles are good for sigma bonds and 120 degrees or odd angles are good for pi bonding. You can see how you got 4 d orbitals involved in pi bonding here and 3 involved in sigma bonding. So you can get a lot of pi bonding out of these kinds of geometries and less sigma. Let's see here. Yeah, and tetrahedral is similar. So let's draw some SALCs for these interactions, okay? So let's do the A1 bonding orbital. We'll call it 1A1. This is the dz squared. Whoa, how did I do that? I still don't really know how to use this pen. There's our sigma bonding orbital between the dz squared and the 5 COs. So let's do the in-plane SALCs. We've got sigma star and pi for xy and x squared minus y squared. So let's do the E prime for sigma here. So we got our metal center, E prime. We got our CO. Mixing this way. And remember that this angle here is 120 degrees between these carbon monoxides. And the nodal planes are 90 degrees. Okay, so those carbon monoxides fall in the unshaded region of that d orbital. And to make a bond, they must also be unshaded. There's also, I'm going to switch over to iron here. I should have done that before. There's also the other orientation of the, I guess it's the dx squared minus y squared. If the one on the left is xy, the one on the right is x squared minus y squared. And in this case, it's the other two COs that point approximately at the ligands. And this ligand over here falls in the nodal plane. Let's do the E double prime, or sorry, the E prime, but this time we're going to draw the pi. You know what, I shouldn't have done that. Let's keep the same shading as above. So how do you fill in these pi symmetry orbitals on the carbon monoxides? You have to consider where the node is. So the bonding interaction is in this part of the lobe. So did I get that right? Yeah. Now, we get a nice fat pi bond with that p orbital there on the left. Again, you have to consider this angle is 120. And this, the d orbital angle is 90, right? So these p orbitals are outside of this, the maximum amplitude along the 90-degree angle. So it's this piece of it that's going to overlap and this piece of it that's going to overlap. Okay. Let's do the out of plane ones here. Let's shade it in to make bonding interactions. Right, this is the E double prime here. So now you have to consider the orientation of the nodal planes in this thing on the right. There's one vertically oriented nodal plane running along Z and sitting in the page of the paper. So there is no p orbital on the left-hand side of this molecule that you can draw right here that interacts with that. This guy, however, you can get this one interacting with it. Similar to these guys. In both cases, these bisymmetry bits always there, part of the game. So dxz and dyz interact with the pi orbitals of the COs that are in the plane and those that are out of the plane. Whereas the dx squared minus y squared only interact with the COs that are in the plane of the three ligands. All right, so D3H is a good pi bonding geometry. So iron pentacarbonyl this guy is D4H, sorry, D3H and D8. It's not C4V. It has 4 out of 5 d orbitals with pi symmetry. And iron 0, D8, is electropositive. Okay. The iron wants to give up its electron density to those carbon monoxides. So it pairs well with pi acceptors, like carbon monoxide. So iron pentacarbonyl is a pretty classic molecule, pretty stable. It's a liquid. You pour it around. It's good stuff. Platinum. Tetrachloroplatinate. It's a wonderful compound. Beautiful blood red color. Not 3-, sorry. 2-. This is platinum 2. It's D4H. It's D8 also. It does not take a tetrahedral shape. It has 3 out of 5 orbitals with pi symmetry. This is a good sigma bonding geometry. Nice right angles pointing right at those lobes. Platinum 2 is relatively electronegative. Everybody has platinum wedding bands. Can't oxidize it very easily. So platinum 2 is electronegative, and it's a good sigma acceptor. So the bonding for that kind of a complex is really dominated by geometries that favor sigma donating ligands, and it's not interested in pi back donation so much. So that's why it's not TD. Rhodium 1 is also D8. It's intermediate. It has intermediate properties, and it supports both sigma and pi bonding geometries. So you get 5 coordinate structures that are both TBP or square pyramidal. Okay. They interconvert. Okay, so rhodium 1 helps to know the periodic table here. Iron is in the upper left of a 3x3 square. Iron is in the lower right of that 3x3 square, and rhodium is in the middle. As you go to the left, they get more electropositive. As you go to the right, they get more electronegative. So when you look at D8 complexes in that square, iron 0, rhodium 1, platinum 2, you're getting to more oxidizing thing as you go toward platinum 2, more electron withdrawing, better sigma bonder. You go to the left, better at pi back donation. Okay, so the geometries that you typically see reflect that kind of thing. All right, so we'll wrap it up here. And Ding and I are going to go